Hi there. Today we're going to talk about parent functions and their transformations. So what is a parent function in a parent graph? It's the simplest graph of a family. So we could have a bunch of parabolas. Remember, those look like U's. The parent graph is the one that's most basic, and then other members of its family have similar characteristics, but maybe it's steeper, or maybe it's over to the right in quadrant 1. Maybe it's down below in quadrant 4. But our parent graph is the one that we base all parabolas around, or all linears around, or whatever function it is, it's the most basic graph of that family. Our transformations can consist of reflections, so we could flip it over the x-axis, over the y-axis. We could, so that it goes down, opens up. We have dilations, that shrinks it or stretches it. We have translations. We could move the graph to the right, to the left, up, down. So our transformations take a parent graph and keep a similar shape, but alter it in a way. So what would that look like on an equation? So the first thing we could do is throw a negative out front of the function. So notice we have a negative sign for this first example out front of a function. And again, in words, a negative out front of the parent graph. What that creates is a reflection over the x-axis. So for example, if I originally had a graph that looked like this, by putting a negative out front, I will now look like that. I am flipping the graph over the x-axis. So that's our first example. Our second example is if I have a negative on the inside of a graph. So if I have a negative on the inside of a graph, what happens is it flips it over the y-axis. So let's pretend I had a normal linear equation. Here's our parent of our linear equation. If I put a negative in front of the function, directly affecting the x, what could happen is that it flips it over the y-axis. And now it would look something like this. Okay? All right, let's look at our next scenario. Our next scenario is if I put a coefficient out front. So for example, if I have a graph, again, we'll go back to our basic sort of parent function. Let's say if I just have the equation y equals x. So that's a nice linear equation. If I put a number out front, for example, now I want to say y equals 5x. What happens there is that it stretches it vertically. So instead of gradually increasing, I have a much steeper slope in this case, and it stretched it vertically. However, if that number is in between 0 and 1, so let's say 1/2, then I'll vertically shrink. It would grow a lot slower. Okay? If I have a value inside the function being multiplied, that's going to create horizontal stretches and shrink. This one doesn't happen as often because usually we factor the value out. But a number on the inside will be a horizontal stretch or shrink. If I add or subtract to the outside of a function, so for example, if I take a parabola, which is in the form of y equals x squared, and I decide to add, and I say, y equals x squared plus 4. What happens to that graph is that it's going to vertically shift. If I add, it moves it up. So instead of my parabola being right at the origin, now it is going to move up 4 units. So notice the change there. if I decided to subtract 4, now my parabola would move down. So it would be more something like this. So adding or subtracting to the outside creates a vertical shift. Lastly, what if I add or subtract to the inside? So let's say I have, again, the parent function of y equals x squared. There it is. What if I decide to do x minus 2 all squared? Well, notice here, if I subtract to the inside of my x, directly affecting the x, it's going to affect the x-axis. So it's going to take that parabola and move it to the right 2 units. So now that parabola has shifted over to the right. If I had added and I had done x plus 2, my parabola would move to the left. So these are the general rules that you want to follow and have memorized. But let's actually go look at some parent functions and get to work. So, some parent functions. One we've already talked about is a constant function, which is a horizontal line. So a horizontal line is always in the form of y equals some constant. Okay? So very basic. Our next one is our linear function, which again we've also discussed. And what you want to memorize is our parent function is simply y equals x. Our slope is 1, the power of course is 1, our y-intercept would be 0. Very basic, okay? So parent function is y equals x. And what that graph looks like is we're at the origin for my y-intercept and our slope is 1. If I look at a transformed function, notice we have more going on. This time we have a 2 out front and we're subtracting 3. Well, if we recall from our chart above, when I multiply out front, that creates a vertical stretch or shrink. Since the value is greater than 1, it's going to cause a vertical stretch. When I subtract to the end of the function, that's going to create a vertical transformation. And because I'm subtracting 3, I'm going to go down 3 units. And let's think about that. If I was to graph a line, we know we plot the y-intercept first, which they're saying is -3, and they say the slope is to go up 2 over 1, up 2 over 1, etc. And I would connect those dots. Let's look at this line now compared to the parent function. What do you notice? It has certainly been shifted down, and there it is, it's down 3 units. It also is a steeper slope. We have vertically stretched it. It's growing faster. So that's how we alter a parent function with its transformations. Let's look at a type of parent function that you may not have seen before, and that is an absolute value function. An absolute value function is always in the shape of a V. Okay? So here's our parent function. Y equals the absolute value of x. Very basic, no other numbers involved. Y equals the absolute value of x. When we are graphing a absolute value function, what we want to do is we want to always find the vertex. And so we can, once we become pros at our transformations, finding that vertex is very easy. But what you want to do is you want to set what's inside the absolute value bars to 0 and solve. That's your x value of vertex. And then what you want to do is identify what is added or subtracted to the end. And that's the y value. So notice in our parent function, that vertex is 0, 0. If I set the inside to 0, x equals 0 is 0. So there's my x value. And what's being added or subtracted to the end? 0. So here we have a vertex of 0, 0. Notice the other information about the parent function of an absolute value. The vertex is at 0, and the slopes are positive 1 and negative 1. So that v goes up 1 over 1, or up 1 to the left 1. And we can kind of look at that based upon out front, really there's a slope of 1 there. So let's look at this transformed function. Let's first talk about finding the vertex. We're going to set the inside to 0, and I get x equals 1. Then I look at what's being added to the outside, and we are adding 4, so that means my y value will be positive 4. So my vertex will be 1, 4. Again, set the inside to 0, and then what is added or subtracted to the outside is my y value. So I would plot 1, 4, and then that slope is still 1. We haven't changed anything out front. So I'm going to go up 1 over 1 to the right, and then up 1 to the left 1 for my other side of the v. Now let's talk about the transformations. Does that make sense? So let's look. If I go back to my chart from up above, when I add or subtract something to the inside of the function, it's a horizontal shift. So here I am subtracting to the inside of this function. So when I subtract, it moves it to the right. So in this case, it moves it to the right one. The plus 4 will move it up 4. Let's compare the two graphs that we have. That vertex, is it shifted to the right one and up 4? Let's look. My parent function would have been at the origin, shift to the right one and up 4. Yep, it's done that. Nothing else should change. So the steepness of that v and the fact that it's going up should look just like the parent, which it does. So absolute value functions are always v's. Finding the vertex is the key piece of that, and then we can use our transformations. All right, and the last parent function we're going to talk about is a quadratic, a parabola, which you have seen before. Remember, a quadratic, like I said, is a parabola, and it has a power of 2. So the parent function of a parabola is y equals x squared. No other numbers involved. For the parent function, what you want to remember is that the vertex is at 0, 0, and then you want to remember 4 other key points. They are 1, 1, and negative 1, 1. So after my vertex, we go up 1 over 1 to both sides, and then the other key points are 2, 4, and negative 2, 4. If you memorize these 4 points, besides the vertex, so 5 points, it'll be really helpful for when you're graphing transformations. Okay, so vertex is at 0, 0, then we are at 1, 1, negative 1, 1, and then 2, 4, and negative 2, 4. So let's look at this transformed graph. In this transformed graph, we have a negative out front. When we have a negative out front, that's a reflection, and it flips specifically over the x-axis. The plus 4 is adding or subtracting directly to the inside. So if I go back to my chart, remember that is a horizontal shift. Because I am adding 4, we are going to move to the left 4 units. So what am I going to do? I'm going to take these 5 points from the parent graph and do exactly what it says. So my vertex was at 0, 0. So I'm going to move that vertex just to the left 4. It's not moving up or down. It's just moving to the left 4. If I reflect that over the x-axis, that doesn't change because my x-axis is right here. That point is right on the x-axis. Okay, now what normally happens after I have my vertex is that I said I normally go up 1, over 1. And I'm just going to quick sketch that. And then I go over 2 and then up 4. And then I would connect my curve. However, we need to remember that we are flipping over the x-axis. So the real graph that we want to have not only is going to be shifted to the left 4, but now it's going to flip. So instead of going over 1, up 1, I'm going to go over 1, down 1. And same thing for my vertex, over 1, down 1. Then for my other 2 points, instead of going over 2, up 4, I'm going to go over 2 and down 4. Again, because of my reflection. So the graph is this solid graph. Okay? All right, so let's do some example practice problems together, and you can try some on your own. So let's describe some of the transformations. On this first problem, what is the parent graph? So remember, the parent graph here, if I look, I see the x squared. My parent graph is just y equals x squared. So what has changed? And let's highlight that. What's changed is that we have a 2 out front and a -5 on the bottom. So what does that 2 out front do? The 2 out front is going to, and again, refer back to your chart if you need to, is that we are going to have a vertical stretch of 2. Okay? The -5 is subtracted at the end. Notice I don't see parentheses with the 5 directly attached to the x. It's at the end, so that's a vertical translation, and that's going to move it down 5. Let's do number 2. What is the parent function of number 2? The parent is y equals the absolute value of x. And what are my transformations? The transformations, let's look at all the changes. We have a negative, we have a +4, and a +2. So that's what's different compared to the parent graph. So we have 3 transformations. The negative out front creates a reflection over x-axis. The +4 is directly attached to that x. So when I'm directly attached to the x, it affects the x-axis, aka horizontal change, and adding 4 moves it to the left 4. And the +2 is at the end. That's a vertical transformation, and that's going to move it up 2. Okay, you try number 3 now. All right, the next set of problems is given a graph, write the correct equation. So the first thing we want to determine is what would be the parent. So what is this shape? This shape is a U. It's a parabola. So remember, parabolas are quadratics. So my parent graph is y equals x squared. We want to transform that based upon the transformations. So what are some of my transformations? Well, let's look. What is one that pops up very quickly? Normally, a parent graph opens up. So this is going down, which means we have a reflection. What else do we have? Usually the parent graph, its vertex is at the origin. This one is up at 0, 4. So we are going to go up 4 units. So we see we have a reflection. We are going up 4. So now we need to see, are we moving to the left or right at all? No, we're still on that y-axis, so there is no horizontal shift. And then we check out whether we have a vertical stretch or shrink. And this one is a little trickier because notice we're going by 2s. So normally what would happen is that I would go over 1 and down 1, And that is actually happening, right? So it's really like a half a block, a half a block. And then what would happen is I would go over 2 and down 4. And I am. 1 block is 2 units, and then down 2 is 4. So there is no vertical stretch or shrink on this problem. So with that being said, we have no vertical stretch or shrink and no horizontal shift. So what we're going to have here is simply a reflection and up 4, which means that new graph will be y equals negative x squared plus 4. All right, you try number 5. Okay, I'll start with you that this is a V. A V's parent graph is absolute value. So the parent graph is y equals the absolute value of x. You determine the transformations. Is there a reflection? Is it going up or down? Is there a vertical stretch? Is there a horizontal shift? Think about that and then create your new equation. Our last situation is that we're going to actually graph based upon our transformations. And instead of making a table of values, we want to actually just go ahead and plot this. So why don't I do number 7 for you? This is an absolute value. So remember the parent graph, I'm going to do in blue. Parent graph is y equals absolute value of x. That parent graph we want to have memorized. Its vertex is at the origin, and the slope of that v is up 1 over 1, and then up 1 to the left 1. So this is what the parent graph looks like. My graph, we're going to do in orange. So what is happening? We have a 2 out front, which is a vertical stretch of 2. We have a plus 4 inside, which is going to move to the left 4. And we are subtracting 3 to the outside, which moves it down 3. Also remember when I find the vertex here, we set the inside to 0. That would give me negative 4. And then the outside value is what's added or subtracted. So my vertex would be negative 4, negative 3. Let's confirm that that would be right based upon my transformations. So let's take my parent graph and let's do the transformations. It says let's go left 4 units, 1, 2, 3, 4, and down 3, 1, 2, 3. Here's my new vertex. And look at that point, negative 4, negative 3. Wahoo, we did it right. But remember, we now also have a vertical stretch of 2. So the graph is still going to open up since there's no reflection, but instead of going up 1 over 1, we are going to go up 2 over 1 and up 2 over 1 and continue with that pattern. So you can notice we have a much steeper and skinnier V. Okay, you try number 6. Recall here that the parent function is going to be a quadratic. And what you need to determine is what are the transformations and take those transformations and change that parent function. Good luck.